Ionizing radiation consists of photons or moving particles that have sufficient energy to knock an electron out of an atom or molecule, thus forming an ion. The photons usually lie in the ultraviolet, X-ray, or gamma-ray regions of the electromagnetic spectrum, whereas the moving particles can be alpha and beta particles emitted during radioactive decay. An energy of roughly 1 to 35 electron volts is needed to ionize an atom or molecule, and the particles and gamma rays emitted during nuclear disintegration often have energies of several million electron volts. Therefore, a single alpha particle, beta particle, or gamma ray can ionize thousands of molecules. Nuclear radiation is potentially harmful to humans because the ionization it produces can significantly alter the structure of molecules within a living cell. The alterations can lead to the death of the cell and even of the organism itself. Despite the potential hazards, however, ionizing radiation is used in medicine for diagnostic and therapeutic purposes, such as locating bone fractures or treating cancer. The hazards can be minimized only if the fundamentals of radiation exposure, including dose limits and the biological effects of radiation, are understood. Exposure is a measure of the ionization produced in air by X-rays or gamma rays, and is defined in the following manner. A beam of X-rays or gamma rays is sent through a mass m of dry air at standard temperature and pressure, where the temperature equals 0 degrees Celsius and the pressure equals 1 atmosphere. In passing through the air, the beam produces positive ions whose total charge is Q. Exposure is defined as the total charge per unit mass of air, or exposure equals Q divided by m. The SI unit for exposure is coulombs per kilogram. However, the first radiation unit to be defined was the Roentgen, given by the symbol R, and it is still used today. With Q expressed in coulombs and m in kilograms, the exposure in Roentgens is equal to 1 divided by 2.58 times 10 to the negative 4 times Q divided by m. Thus, when X-rays or gamma rays produce an exposure of 1 Roentgen, 2.58 times 10 to the negative 4 coulombs of positive charge are produced in 1 kilogram of dry air. Or, 1 Roentgen equals 2.58 times 10 to the negative 4 coulombs per kilogram. The concept of exposure is defined in terms of the ionizing abilities of X-rays and gamma rays in air, but it does not specify the effect of radiation on living tissue. For biological purposes, the absorbed dose is a more suitable quantity because it is the energy absorbed from the radiation per unit mass of absorbing material. The absorbed dose is equal to the energy absorbed divided by the mass of the absorbing material. The SI unit of absorbed dose is the gray, which is 1 joule per kilogram. The equation for the absorbed dose is applicable to all types of radiation and absorbing media. Another unit is often used for absorbed dose, namely the rad. The word rad is an acronym for radiation absorbed dose, and 1 rad equals 0.01 gray. The amount of biological damage produced by ionizing radiation is different for different kinds of radiation. For instance, a 1 rad dose of neutrons is far more likely to produce eye cataracts than a 1 rad dose of X-rays. To compare the damage caused by different types of radiation, the relative biological effectiveness, or RBE, is used. The relative biological effectiveness of a particular type of radiation is the ratio of the dose of 200 kilovolt X-rays needed to produce a certain biological effect to the dose of the radiation needed to produce the same biological effect. RBE is a dimensionless quantity, just a number. The RBE depends on the nature of the ionizing radiation and its energy, as well as on the type of tissue being irradiated. Here we list some typical RBE values for different kinds of radiation, assuming that an average biological tissue is being irradiated. First, notice that an RBE value of 1 for gamma rays and beta minus particles indicates that they produce the same biological damage as do 200 kilovolt X-rays. Alpha particles have the largest RBE value at 10 to 20, and therefore do the greatest damage to biological tissue for a given dose. Next are protons and fast neutrons with RBE values of 10. The RBE is often used in conjunction with the absorbed dose to reflect the damage-producing character of the radiation. The product of the absorbed dose in rads, not in grays, and the RBE is the biological equivalent dose. The unit for the biologically equivalent dose is the rem, short for Roentgen equivalent in man. Everyone is continually exposed to background radiation from natural sources, such as cosmic rays, which are high-energy particles that come from outside the solar system, radioactive materials in the environment, and radioactive nuclei within our own bodies, primarily carbon-14, potassium-40, and radon. Here we list the average biologically equivalent doses received from these sources by a citizen in the United States. According to this table, radon is a major contributor to the natural background radiation. Radon is an odorless radioactive gas and poses a health hazard because, when inhaled, it can damage the lungs and cause cancer. Radon is found in soil and rocks and enters houses via a mechanism that is not well understood. One possibility for indoor radon entry is through cracks and crevices in the foundation. The amount of radon in the soil varies greatly throughout the country, with some localities having significant amounts and others having virtually none. Accordingly, the dose that any individual receives can vary widely from the average value of 207 millirem per year given in the table. In many houses, the entry of radon can be reduced significantly by sealing the foundation against entry of the gas and providing good ventilation so it does not accumulate. In addition to the natural background of radiation, a significant amount of human-made radiation has been added, mostly from medically related sources. Among these sources, CAT scanning is the major contributor, as seen in this table. The effects of radiation on humans can be grouped into two categories according to the time span between initial exposure and the appearance of physiological symptoms. The first category includes short-term or acute effects that appear within a matter of minutes, days, or weeks. And the second category includes long-term or latent effects that appear years, decades, or even generations later.